Welcome to EZMathTV. We're going to talk about rational functions today. This will wrap up our chapter on polynomial functions. Um, we're going to do two things. We're going to see an example of a rational function that's based on a toolkit function and use that to find the domain, graph it, and then identify any prominent features, key features. The key features of rational functions are in the form of what we call asymptotes. So that's why you see the word asymptote here. We're going to define what that is, and that is the prominent or key feature of a rational function. And then we're going to see some general rational functions that are not easily based off of any toolkit function that we have. So we'll describe any asymptotes and prominent features of those, and also figure out what the domain is as well. So what is a rational function? It is a function f of x that is a ratio or quotient of two polynomials, p of x divided by q of x. So both the numerator and the denominator need to look like polynomials. The domain of this function will consist of all inputs x for which the denominator is not equal to 0. So here's an example. Let f of x equal 1 over x minus 3. We're going to graph it, and if possible, what is the toolkit function that it's based off of? And then we're going to identify the domain. So when I put it into Desmos, here's what the graph looks like. If you also graph the function that's similar to this, 1 over x, 1 over x almost looks exactly like it, except that this is a shift of that graph 3 units to the right. So we would basically state then that the toolkit function that this is based off of must be, in fact, f of x equals 1 over x. So 1 over x and 1 over x minus 3 are in the same family. And the function that we're looking at here is just a shift of that one 3 units to the right. So that also affects the domain. Since the domain of 1 over x is all values of x except for 0, then the domain of this one is probably going to be all values of x except for 3, because it's shifted 3 units to the right. And as you can see, there's like a dotted line there that shows us that value of x that has to be removed from the domain as well. So the way we write that is x is not equal to 3 is what we call set builder notation. Or if you're supposed to use interval notation, then we would use parenthesis negative infinity comma 3 union parenthesis 3 comma infinity parenthesis. So anytime you have to take the real number line and remove a single point, this is the interval notation for that. You see the minus infinity and infinity on the left and the right, and then the point that you're removing is in the middle here, okay? And use parentheses around both intervals. So that is the domain of this function. And the dotted line just happens to be a vertical line. And that vertical line is a vertical asymptote. So let's define what a vertical asymptote is. For a rational function, f of x equals p of x divided by q of x, where p of x and q of x are polynomials with no common factors. So when we have a rational function, we need to be careful, because we need to make sure that there are no common factors between the numerator and denominator, especially if we're being asked to identify any vertical asymptotes. So as long as there are no common factors, the graph will have a vertical asymptote at x equals a, or x equals some number, whenever the quantity x minus a is a factor of the denominator. Okay? So factors of the denominator are going to determine where those vertical asymptotes exist. So let's look at an example. Determine the vertical asymptotes of this function. F of x equals 2x minus 11 over x squared plus 2x minus 8. And there are two options for this. We're going to see both options. Option 1 is to graph it and see if we can locate the vertical breaks in the graph just by looking at the graph. All right. The dotted lines that you will see are going to indicate what those vertical asymptotes are. And here's what that graph looks like. If you take a vertical object and just move it along, pass it over the graph, you can actually see where those splits occur. And we're not concerned at all about any other features of the graph except for where those two vertical asymptotes or more, where those vertical asymptotes are. Okay. This particular graph just happens to have a relative minimum as well, somewhere really close to 0 there. But nobody asked us to find that, so we're not interested at all in that. The two vertical asymptotes are at the lines x equals -4 and x equals +2. So those are the two orange dotted lines that we are interested in here. That's it. If you're not comfortable looking at the graph, then there's another way. Option 2 is to factor the denominator. Using wolframalpha.com is what we're going to do. And then once you do that, we're going to set it equal to 0, just the denominator, and ignore the numerator. So that makes it pretty easy to work with. You just focus on the denominator only. So if we notice here, the denominator is x squared plus 2x minus 8, and that factors into x plus 4, the quantity, times x minus 2. So zip it, which means use the zero product property. Set x plus 4 equal to 0, and you get x equals -4. If you set x minus 2 equal to 0, you get x equals 2. And notice I completely ignored the numerator. I'm not dealing with the fraction at all. I'm just looking at the denominator only and setting it equal to 0. So those are your two vertical asymptotes, x equals -4 and x equals +2. So it's not as hard as it looks because you're not dealing with the entire fraction. You're not dealing with the entire function, just the denominator of the function. The other type of asymptote that we need to discuss is the horizontal asymptote, which has to do with end behavior of the function. There are two horizontal asymptotes that we need to consider. The first one occurs when the degree of the numerator and the denominator are the same. Again, the first type of asymptote occurs when the degree of the numerator and the denominator is the same. An example of that is shown here. F of x equals 3x minus 8 divided by x plus 2. Both the numerator and the denominator have a degree of 1. So when that happens, you take the highest powers of x and divide them. So divide the leading terms, and the x's should cancel. If the x's do not cancel, then you don't have the same degree in both the numerator and denominator, or you accidentally didn't choose the highest power of x. So the leading terms are the highest powers of x. 3x divided by x is 3 divided by 1, which is 3. And so the horizontal asymptote for this function is y equals 3. Not x equals 3, y equals 3, because it's horizontal. Remember, horizontal lines have an equation y equals something. So that describes the end behavior of that function. What about the end behavior when we have the degree of the denominator that is bigger than the degree of the numerator? So again, the degree of the denominator is bigger than the degree of the numerator. And it doesn't matter if it's only 1 degree more or 5 degrees more. It just has to be more. So An example of that would be f of x equals 4x plus 1 divided by x squared minus 9. The degree of the denominator is 2. The degree of the numerator is 1. So there's no need to divide here. This is actually easier because when the degree of the denominator is bigger, all we have to do is say, okay, it has a horizontal asymptote of y equals 0, which is basically the x-axis. Okay, that horizontal asymptote is telling us what's happening towards the very ends of the function. All right. So here's the summary of that. You have the two types of horizontal asymptotes. One is when the degrees are the same. The other one is when the degree of the denominator is bigger. Okay, but they are both y equals a number. So when the degree of the numerator is bigger, then there is no horizontal asymptote, and you don't have to do anything there. There just is no horizontal asymptote. There could still be a vertical one, though, but no horizontal one. So let's look at an example where we're being asked to find all the asymptotes, both the horizontal ones, or the horizontal one, and any vertical ones that might exist. And it's also asking us to state the domain. So this function is f of x equals 2x plus 3 divided by x cubed minus 2x plus 4. So what I'm going to do is I'm going to consider the horizontal asymptote first. Since the degree of the denominator is bigger than the degree of the numerator, 3 is bigger than 1 basically, then we have a horizontal asymptote of y equals 0. So that's pretty straightforward right there. There's not a whole lot of thinking involved. If the degree of the denominator is bigger, then all you have to do is say, yes, there's a horizontal asymptote and it's y equals 0, which is basically the x-axis. So the only work that's involved is in finding any vertical asymptotes that exist. So there can be as many of these as there are zeros of the denominator. And we're going to use wolframalpha.com to find them. So in wolframalpha.com, in the solve window, or the solve window, I'm just going to type solve and x to the third power minus 2x plus 4 equals 0. You'll notice I completely ignored the numerator and I only typed in the denominator equal to 0. Okay? That's important. So ignore the numerator completely. Wolframalpha.com tells me that the equation I typed in was x to the third minus 2x plus 4 equals 0, and the results are given here. So we're going to ignore any imaginary solutions. Those are solutions that have an I in them. And it just so happens that there are 2 of those here, so we're ignoring those. And we're only going to use the solution x equals negative 2. So that is our vertical asymptote, x equals negative 2. This also gives us numbers to exclude from the domain. So we're ready to write our conclusion. The horizontal asymptote is y equals 0, which is the x-axis. The vertical asymptote is x equals negative 2. The domain of the function is x not equal to negative 2. So in interval notation, we write that minus infinity comma negative 2, parenthesis, union, parenthesis, negative 2 comma infinity. And make sure you put parentheses around both of those half intervals or half lines. Okay? So that answered the question. And so it was not as hard as it looked, because we have technology to do the work for us. Example 4 tells us it wants us to graph this function, and then there's going to be a question that it asks. So graph the function g of x equals 2x squared plus 1 over x squared. So I went ahead and put it into Desmos.com, and the graph looks like this. So the graph has two like boomerang shapes. I call these boomerang shapes. So we have the two boomerang shapes here, and it looks like there's some symmetry. It's symmetric with respect to the y-axis, and you can tell that it is because in the function we have an x squared and an x squared. So whenever the powers of x are even, we have symmetry with respect to the y-axis. Can the asymptotes be identified from the graph? The answer is sometimes it can when the location is obvious, when you can actually read the graph and you can see where those numbers are, then yes, you can answer it from the graph. So here we have a vertical and a horizontal asymptote. The vertical one is the line x equals 0, which is basically the y-axis, and the horizontal one occurs at y equals 2. Sometimes you can adjust the zoom level, and that might be able to help you even more. Here's what our two boomerangs look like if we zoom out. But we just need to be careful, like identifying what the numbers here are on the graph, because because of our zoom level, each square is two units long or 2 units wide. So we have to be careful about like counting units. But again, this zoomed out graph just illustrates that the vertical asymptote is in fact at x equals 0, and the horizontal asymptote is in fact at y equals 2. So that really shows you that end behavior there going to the left and to the right. And it really shows you where the break is occurring at 0 and forcing the graph to be up towards infinity, and getting on both sides of that of 0, of x equals 0. So just to summarize, when we have rational functions, we first want to make sure that there are no common factors between the numerator and the denominator, okay? So make sure there are no common factors between the numerator and the denominator. Once we have made sure of that, a vertical asymptote occurs at any x values that make the denominator 0. And then we have a horizontal asymptote when the degree of the numerator is less than the degree of the denominator. So if the denominator is a bigger polynomial, and that's the x-axis. If the degree of the numerator and the denominator is the same, then we have a horizontal asymptote that occurs either above the x-axis or below the x-axis. For that, we just have to divide the highest powers of x, and whatever we get when we simplify that, that's your horizontal asymptote. So like, subscribe, comment down below, and I'll see you in the next video.